In the previous lecture, we studied regarding the Markov source. So you know what is a Markov source, right? It's a independent. Sorry, here the symbols generated one after the other will depend on the previous symbols generated. And then we also saw the state diagram given the transition probabilities, right? Because when we talk about a Markov source, the different symbols emitted by the Markov source will depend on the previous one. So we need to move from one state to another state, or one symbol to another state, another symbol. So there is something called as transitional probability or conditional probability. So we saw regarding the state diagram. So state diagram mainly represents the different transition probabilities. And also we learned how to draw a tree diagram given the state diagram, right? So tree diagram will help us to determine the total probability or entropy when we have multiple symbols, a large symbols generated by the Markov source. The tree diagram is much more helpful in determining the total probability of the symbols or that long message. And then we saw the state entropy, because in a Markov source we have dependent symbols or messages. Then each state or each symbol from its current state will move to the next state. Then the entropy of every state we need to determine. That's the present state we need to determine. So HI indicates the state entropy. So that is nothing but the conditional probability of moving from the present state to the next state, log 1 by Pij. This is computed for all the states that is possible to transit from the state I. So we have the summation here from J to N. Similarly, later on we found the source entropy. That's the total entropy of the source, Markov source. That is nothing but the summation of entropy of different state entropies. So HI multiplied by PI. PI is the original probability of occurrence of a particular state or symbol multiplied by its state entropy. So we will compute this for all the states. Then also we determine the average information content, that is GI. That is nothing but 1 by n times probability of the message, log of 1 by probability of the message. So here n is what? N is the length of the symbol, right? And also we ended our discussion with this general understanding, that is G1 is greater than or equal to G2 is greater than or equal to H. So this is a very key takeaway from the previous lecture. That is, when the messages are of smaller size, then the average information content is much greater than when the messages are larger in size. And if you consider the entropy will occupy least number of bits per symbol. Okay, and then we will move on to the today's lecture. So in the today's lecture, we will be seeing regarding the source encoding process. So this diagram, if you remember, in the first class, I mentioned to you that there is a data generated from different sources, maybe a camera generating multiple photos, or a video source that generating multiple videos, or teletypewriter generating different symbols or messages, a person speaking different sentences, and so on. These are the different data that are generated normally in the physical world. And this data we want to transmit from this particular place to some other place. For example, I'm talking here, I want to transmit this data to some other people, some other user who is located far away from me. In that case, I need to send the data through electronically. So mainly in this time we are talking about the digital communication system. So here the data from the source comes to a block called as a source encoding or source encoder, where the data, whatever may be its form, maybe it's a video or a photo or just text messages, alphabets, etc., has to be converted into bits. And then it goes to the channel encoding. Finally, it goes to the channel, and then the reverse processes will take place at the receiver. Okay, so right now we will limit our discussion to only this block, that is source encoding. So as I said, what's the main function of source encoding? Source encoding will mainly convert the message or data that comes from different sources into digital format. It will assign a digital pattern for every message. For example, you consider 4 photos. We have 4 photos. Photo 1, 2, 3, and 4. We want to transmit from this source to somewhere else. So what do? We assign the first photo by one code, maybe 00. The second photo we represent as 01. Third photo 10. Fourth photo 11, and so on. So that when it is transmitted to the destination here, this can easily identify based on these codes. Okay, if it is 00, oh, it's a first photo of a place. 01, it's a second photo of a person, and so on. Anything. Okay, just an example. So source encoding will mainly deal with that. But it is not only that. Source encoding must try to represent the data by unique code words, and these code words must be intelligent. For example, the example what I gave right now is very generic. For example, I said 4 photos, so you represent each by 2 bits, 00, 01, 10, and 11. So that is very common. We don't need such kind of easy methods at the source encoding. We need to find out some algorithms so that we can represent each data by different codes, but these codes must be of minimum size. I will tell you maybe as we proceed, or maybe at the end of the lecture, why we are talking about minimum size. I said the source, when we code it, they should be of minimum size. So in that way, intelligently it has to do the coding process, encoding process. So different algorithms, what we discuss, maybe today we'll discuss one algorithm. They all run in this block, source encoder block. So they will always try to represent the data by different bits, different bit patterns, and these bit patterns must be good enough or should be intelligent. So right now, I will move on to the definition of source encoding. What is source encoding? So it's a process of encoding the data where the data emitted by the source is represented in binary. That is what I mentioned, right? For example, a data. There are 3 symbols generated by the data source. For example, A, B, and C, and so on. How do we represent it? The source encoder will represent A as 11 and B as 01 and C as 00 and so on. This is just an example, and it's a very generic example to start with the discussion of source encoding. Okay, we will move on to the next slide. So here, a few more details regarding the source encoding. So the first one is the performance of the source encoder, or whichever algorithm that runs in the source encoder, is measured. Its performance is measured in terms of coding efficiency. So anything we perform, we measure it with the help of efficiency, right? How much it is efficient in performing what's the objective is, or meeting the objective. So that is called the coding efficiency. There is an equation to find out the coding efficiency. I think at the end of this course, end of today's lecture, we will work out an example, and that shows how to find out the coding efficiency. And then source coding can be achieved in different ways. As I said, the source encoder is a general block or general idea. You can run your own algorithm to represent the bits. For example, in the example where I mentioned A, B, C are the different messages, and we represent A by 00, B by 01. It did not be the case, right? Maybe I represent A by just 10. Instead of 2 zeros, I just represent it by 10. But B, I represent it by maybe 2 bits, 10, and so on. So there are different ways of doing this, and we will study some of them. But today we will just limit our discussion to one of those algorithms, very important algorithms. Okay, so the important one is Shannon's encoding algorithm. So if you remember the first lecture, I mentioned about Shannon. Shannon is considered as the father of information technology, right? Information theory and coding, or in general information technology. Okay, so Shannon's encoding, what's the idea? Now we'll see what's the Shannon's encoding algorithm. So in this lecture, first we will study the theory of Shannon's encoding, and then if you cannot understand the theory, I have an example for you to understand it more clearly, and then you should be able to understand it to the 100%. Okay, now we will see some theoretical discussion regarding Shannon's encoding. So what is the scenario here? What's the idea here? So the output of a source will consist of many messages. This is what I mentioned. Any source, maybe a camera or a person speaking, there will be many messages emitted from the speech or emitted from the camera and so on. And each message may consist of many symbols, n number of symbols that vary. They will have the varying probability. For example, if you consider uh, a sentence, in that sentence there will be many alphabets, right? Those alphabets will vary in their occurrence. The occurring probabilities will vary. For example, if you should consider any English sentence, there will be more number of A's or vowels than Z or X or K and so on. Those letters rarely appear, right? Maybe maybe X or Z. Those letters rarely appear, whereas A, O, all those letters occur very frequently. So that's what I mentioned regarding if the message is something like a sentence, then a sentence will have different letters. They will have varying probability. Some letters will occur very frequently. Some letters will occur seldom. Okay, then thus a source encoder should try to replace each message by a unique binary code. So this is what I mentioned in the previous slide while showing you the diagram of source encoder. The source will emit different messages like A, B, C. But what is the function of source encoder? It has to represent every message by a unique binary code. Okay, so now we have to take care about this. That is HN prime. That is what average bits per symbol of coding should be close to GN. That's the average information content, right? GN we have seen. So basically, that is nothing but HN prime is nothing but 1 by n times summation of ni pi. So pi, you know, that's the probability of any symbol or message. What is ni? Ni is the length of the code word ci. So when we represent a message by a code word, for example A, we represent it as 00. So now 00 is nothing but the code word ci, and ni is the length of the code word. See, this code word has how many bits? 00, so 2 bits, right? So length is 2, ni is 2. So this basically says, this term mainly says what is the weightage of this particular symbol. So this says it appears 2 times with the probability of 0.4 or 0.3 and so on. And that we compute for all the symbols want to study. And then we take the average. So that should be almost closely or nearly equal to Gn. We know Gn is the average information content. That is nothing but pi log 1 by pi multiplied by 1 by n. Okay, so these are the theoretical ideas behind Shannon's encoding. But now we will see, but at the end of the discussion, you must be able to appreciate this, why we have this kind of relations and all. And but right now we will move on to the algorithm, Shannon's algorithm. What is actually Shannon's algorithm is. We will see the different steps of this algorithm, and then we will move on to the example, and that will be today's lecture. First, in case of Shannon's algorithm, that is called as Shannon's first encoding algorithm, because Shannon with somebody else, they also had another algorithm. So this is Shannon's first encoding theorem. So what is the input in this case? Source alphabet, yes, and corresponding probabilities. What's the meaning here? There is a source that emits different alphabets or different messages, different photos, different videos, and so on. It just in general we'll call it as different messages. Okay, so the set of messages is represented as S. Maybe S is equal to A, B, C. Okay, they are A, B, C are the different messages, and they will have different probabilities. For example, A will have a probability of 0.2, B will have a probability of 0.5, and so on. So this information we know in case of Shannon's first encoding theorem. If this information is known, then how can we code these messages? That idea is nothing but Shannon's first encoding theorem. So to do that, we have the different steps. First step. In the first step, arrange the probabilities of the messages in non-increasing order. So input is what? We have different messages and their probabilities. We know their probabilities. So with these probabilities, we will, in the first step, what do? we'll just arrange them in the non-increasing order. You know what is non-increasing order, right? That means decreasing order, highest probability first, lowest probability last. So that is what we do. We have a set of probabilities here, we just sort them. Okay, that's very easy, right? Now we will go to the second step. Second step is compute the length of the code word Li for each symbol. How to find the length of the code word? It is given here. The length of the code word Li should be greater than or equal to log of 1 by pi. Since we know the pi, see here we know the probabilities, that is the input given. Since we know the probabilities, can we find out log of 1 by pi? Of course, you know how to find out log of 1 by pi. We are talking about log 2. I'm not going to tell you again and again. In this course, we will use log 2 unless I specify it as something else. So log 2 1 by pi, we can easily compute. So you get a value here, right? Maybe log 2 of 1 by 0.4. What's the value? Maybe it is 1.7. I don't know. Just saying 1.7. Assume it as 1.7. Then what's the length of the code word Li? That must be greater than or equal to 1.7. That means it should be the next higher integer. Suppose this value is 1.7, we are making it as 2. If this value is equal to 1.3, we are making it 2. If this value is equal to 0.8, we are making it the next higher integer, that is 1. If it is already equal to 1, then it is 1 itself. So it is Li should be greater than or equal to this value. That means we want to convert the value here into the next higher integer. That is the length of the code word Li. So we know the probability. We just calculate the value of Li for every symbol, SI, or every message. That's the second step. That is also easy, right? It's easy computation. Okay. Now we will move on to the third step. Now we have to define some of the parameters from the probability set. Probability set is the input. We know already. They have given us all these probabilities. So we have to find out some parameters. What parameters? Parameters are called as Q parameters here. First one, for the first message or for the first symbol, the Q1 value is 0. That is by default, its value is considered as 0. And then we find out Q2 because the third step says we have to define some parameters. We have to define many parameters here. The first parameter is Q1, that is 0 by default. The second parameter is Q2. How to find out Q2? Q2 is equal to P1. What is P1? P1 is the probability of the first symbol or message. Since we know the set of probabilities, right? We already know what are the elements of the probability set. I said maybe 0.4, 0.3, 0.2, and so on. So first one, first probability of the first message, that itself is Q2. And is it equal to Q1 plus P1? P1 here plus Q1. What is Q1? 0. So 0 plus P1 is P1 itself. So this equation has meaning, right? Okay. Then we will go to find out the third parameter, that is Q3. What is Q3? Q3 is equal to P1 plus P2. Is it equal to Q2 plus P2? Of course, yes, because P2 is here. And what is Q2? Q2 is this. That is equal to P1. So P1 plus P2 is equal to P1 plus P2. Okay. So in general, Q3 is equal to P1 plus P2. That means probability of the first symbol and probability of the second symbol. So can you predict what is Q4? So someone, if knows the answer, please unmute and answer this question. Because it will follow a pattern here. The first one is 0. Second one is equal to probability of the first one. Third one is equal to probability of first one and second one. What is Q4? Elvin, can you try? Or someone else? Whoever tries, I will give you 0.5 marks. That's a bonus question. Please tell me your name and tell me the answer. You have 1 minute to answer this question.
So Q3 plus P3.
Your name?
Ashika.
Okay, from A section, right?
Yes, sir.
Okay. Yes. So Q4 will be P1 plus P2 plus P3, right? That is equal to Q3 plus P3, right? Yes, very good, Ashika, and you'll get 0.5 marks. I will remember that. And this 0.5 will be added directly to your continuous evaluation. Okay. Similarly, you go on Q4, 5, 6 until Qn plus 1. Qn plus 1 is equal to 1, right? Because what is n? N is the total number of symbols. We have started from Q1. So when we reach the Qn plus 1, it of course should reach to 1 because the first one we consider as 0. We are counting from P1 here, P1, next P1 plus P2, next P1, P2, P3, next P1, P2, P3, 4, P4, and so on. Finally, P1 plus P2 plus P3 plus Pn. So, you know, sum of probabilities will be equal to 1, right? Okay, so this is very easy, right? Because you just need to compute these Q1 to Qn plus 1 or whatever last number. You just need to know the probabilities. We already know the probabilities. Accordingly, we can compute. So third step is also simple, right? Then we will move on to the fourth step. You should be very careful here. I mean, you have to make a careful observation here. So the fourth step is expand Qi. Qi means maybe Q1 or Q2, whatever. In general, Qi in binary. Did you notice that Q values will be in a decimal? Because they are nothing but the sum of probabilities. Probabilities in a decimal, right? For example, 0.4 or 0.7 or so on. They are in decimal. You convert it into binary. When you convert it into binary, how many bits you need to represent it by? That is equal to Li number of bits after the decimal point. Do you know how to find out Li? Have you seen that? If you remember second step, we found Li in the second step, right? That is equal to greater than or equal to log of 1 by pi, right? So with the it's in once it is converted into binary, you should convert it into so many number of bits after the decimal point. For example, maybe your binary value becomes 0.1110. Now, based on your Li, maybe Li value is equal to 2. Then you have to just represent it as 0.11. That means after the decimal point, you just need to have only so many number of bits, maybe 2 bits or 3 bits and so on. So that is the fourth step. And in the fifth step, what? The bits places after the decimal point of Qi are the code word. So when you are done with the fourth step, you already got the code word. So you have to just pick it from your answer. Where is the code word? Code word are nothing but whatever bits you have after the decimal point. When you convert it into binary, they are the code words. Okay. So these are the different steps of Shannon's encoding algorithm. So someone please tell me if you understood these steps or my voice is audible, because I just want to check in between. If it's not audible, then I will not go further. Is my voice audible?
Yes, sir.
Audible, sir.
It's very good. So these are the different steps, but now I will go to an example. I think maybe you have some questions. So instead of discussing regarding this general step, better is to see an example. And if you have pen and paper, you can try to solve it. Okay, or you just participate in this discussion, so you will get the idea. So I will move on to the example. So in this example, I will discuss all those 4 or 5 steps in detail. Okay, so right now we have a question here. A source emits different alphabets. The set S are the set of alphabets or any messages. But in this example, I have considered this as alphabets. What are the alphabets? A, B, C, D. These are the 4 messages generated by the source. What is the probability of these messages? 0.1, 0.2, 0.3, 0.4. That means A is 0.1, B is 0.2. Similarly, D is 0.4. That's the meaning. Okay, this is the input given. You should know these inputs. Then only you can use a Shannon's encoding algorithm. Okay, since we know these things, then we will use, the question is, encode these symbols using Shannon's algorithm and find the source entropy and redundancy. How to do this? Okay, so the first step. What is the first step? First step is to arrange the probabilities in the non-increasing order. So you know the probabilities here. You arrange this. Is it in the non-increasing order? If it is already there, very happy. Otherwise, you just sort it in the non-increasing order. That means decreasing order. Decreasing, highest first, lowest last. So 0.4, 0.3, 0.2, 0.1. So 0.4 is what? 0.4 is D, right? 0.4 represents symbol D. So accordingly, your symbols, just you need to remember that what probability is for which symbol. Okay, our work is only with the probabilities. Okay, so first step is to arrange the probabilities in non-increasing order. That is done here. Okay, and we'll go on to the second step. Do you remember what is the second step? Now you have to find out the size of the code word. So minimum value of Li, that's the size of the code word, such that Li is greater than or equal to log of 1 by Pi. Pi is what? Probability of every symbol. How many symbols we have? 4 symbols, A, B, C, D, right? So you know how to find out Li. I will just give some hint here. L1, the first symbol, D, right? What's its probability? Log of 1 by 0.4, right? How much value? Log is log 2. You can just use your calculator, or if you can do your mathematics by yourself, you just do it. And that is log of 1 by 0.4 for the first symbol. What's the value? You will get it as a 1.321. Okay, so this is the value of Li, but we have to meet this condition. Li must be greater than or equal to log of 1 by Pi. So right now the value is 1.321. So we need to upgrade or round it off to 2, the next higher integer, greater than, okay, greater than 1.3. That means 2, the next higher integer. Similarly, you find L2. Can you find L2? L2 must be greater than or equal to log of 1 by P2. That is the equation. So you know what is probability of the second symbol, that is C, that is 0.3, log of 1 by 0.3. That will come some fractional value, maybe 1.2 or something. Then you will make it to 2. Okay, so this value, what is exact value, you find it by yourself. It should be around 1.2 or something. Then you have to, the next possible value to round it is 2. Okay, next L3. What is the value of L3? Log of 1 by 0.2. So that comes to 2.3. Right? Maybe this is 1.8. So we have made it as 2. Okay, this is 2.3. So when it is 2.3, how to round it to 3? Okay, and the next L4, 1 by P4. What's the value? 1 by 0.4. So you will get some value here, but we will round it to 4. Okay, so this is the length of the code word. Right now we have not found what is the code word, but we just got what should be the length of the code word, right? So the first code word will have only 2 bits. Second code word will also have 2 bits. Third code word will have 3 bits. Fourth code word will have 4 bits. But we don't know which bits. I mean, of course, the bits will be 0 and 1. We don't know where is 1, where is 0 if the size is 4. It may be 0101 or 1110. We don't know what combination. Okay, we will find it out at the end of this example. Okay, now I move on to the third step. Now you have to find out the different parameters, that is Qi. We have Q1, you know what is Q1. By default, it is 0. What is Q2? Q2 is P1. What is P1? Probability of the first symbol, 0.4. What is Q3? Probability of the first and second, 0.4 and 0.3, that is 0.7. What is Q4? First, second, third, 0.4, 0.3, 0.2. What is Q5? Probability of all P1, P2, P3, P4. That will be 1. Okay. So basically, this is Q of n plus 1. N is equal to 4 in our case. We have 4 symbols. So n plus 1, that is 5. So that will be 1 because we are starting our count from Q2, right? So we'll have Q of n plus 1. Okay. Now we will move on to the next step. What's the next step? Represent Q1 to Q4 in binary, because what? Q1 represents the first symbol, Q4 represents the last symbol. We have only 4 symbols in binary. So we have, this is a what, decimal value, right? Is it decimal value? Yes, all the Q values are decimal, 0.4, 0.7, 0.9, 1, 0, etc. So we have to convert this into binary. So how to convert? The first value is Q1, right? What's Q1? Q1 is 0 in decimal. Binary also it is 0 only. But I have written here 0.00 in binary. Why it is 2 zeros here? Do you know why? Because the L1 value is 2. Do you remember L1 value? Maybe I can just go back and show you. Please remember here, L1 value is 2, L2 value is also 2, L3 3, L4 4, okay? 2 2 3 4. This is what we need for the next calculation. Here. So Q1 value, decimal it is 0. So we have converted into binary, that is 0.00000. But I have restricted it to 0.00. Why? Because these binary codes length should be guided by Li. So Li is equal to 2. So I have only put 2 zeros here. So Q1 corresponds to what? That corresponds to the symbol, first symbol D, and its code word is 00. A yellow color here, whatever we have, that becomes the code word. Next, Q2. Q2 is what? It is 0.4. In the previous slide, we have noticed what is the value of Q2, right? It is 0.4 in decimal. How to convert it into binary? You know how to convert decimal into binary, right? Just multiply by 2, keep multiplying until you get 1. Yes, okay. So that is very elementary. You can just practice by yourself. So, okay, the overall idea here is to convert that decimal into binary. That is 0.4 becomes 0.011000 and something, a large sequence, maybe 4 or 5 bits here. But we are restricting our size here to 2 bits, only 2 bits after the decimal point. So I'm not writing 0.01100 and so on. I'm just writing 0.01, only 2 digits. Why? Because L2 size is also 2 bits, right? That is what we have seen. And that L2 corresponds to what? The second symbol C. So second symbol C's code word is 01. Just pick up from here and assign it here. Next, we will go to Q3. What's the value of Q3? Q3 is 0.7 in decimal. How to convert? You convert it into binary. Maybe it is 0.10111010 and so on. But we will limit this to 0.101. Why? Because L3 value was 3, right? So we will cut this only up to here, 101, 3 bits after the decimal point. So 101 here, yellow color, that becomes the code word for symbol B. Next, Q4. What's the probability of Q4? 0.9, and that's in decimal. Here 10 indicates it is in decimal. Okay, it is not multiplying 10, just indicating the index that it is 10. Now I'm converting it into binary. What's the binary equivalent of 0.9? 0.111010 and so on. So, but I'm limiting this to 4 bits here after the decimal point because L4 was 4. So only 4 bits in binary. L4 corresponds to what? Symbol A. So A's code is 1110. That is what is here, yellow color. I have just copied here. So we know these are the code words. This is actually the fifth step. I have combined here. Okay, instead of writing from here to here as a separate step, I have just combined here. That looks easy. So this is the last step, and these are the code words. So when the source emits symbols like D, C, B, A, or A, B, C, D, whatever, in any order, then A will be represented by 4 bits, 4-bit code word. Instead of transmitting A, the encoder will transmit 1110. Instead of transmitting B, it will transmit 101. Instead of transmitting C, it will transmit 01. Instead of D, it will transmit 00. This is how the encoder will perform the encoding of the data or message. For example, the first sentence, second sentence, third sentence, fourth sentence. First photo, second photo, third photo, fourth photo. Okay. Instead of representing that as messages itself, it is represented in binary, because we are dealing with the digital communication. We want to transmit through digital medium and process it digitally, store it digitally, everything. So you are interested in bits, bit pattern. Okay, now from this discussion, is there any key point to remember? I will just give the hint here. It's one important key point. Please read this sentence. And after that, I will go for the question and answers. So the very important point of the Shannon's encoding algorithm is here. So message with the high probability will be represented by the code word of short length, which is a message with a high probability here. 0.4 is the highest probability. The message is D. That is represented by just 2 bits. Similarly, this one is 0.3. It's also high, not very high, but second high. That is also represented by 2 bits. Now, as the probability reduces, your code size increases, right? This is what the general observation. What's the meaning here? So if we want to transmit some message, these messages which are having the high probability, they will occur very frequently. And these messages have a very low probability, will occur seldom, once in a while. Then we can afford to transmit such messages which have a low probability by good number of bits, no problem. Because they occur once in a while. If you spend more number of bits, it's not a burden to me. But these cases which have high probability, they occur very frequently. I have to transmit them very, very often. And if I spend or someone spends more number of bits for these messages, then we have to spend so many bits, because so many times we have to transmit such messages. That is not a good situation for me, for any transmitter, right? Because we will be spending so many bits. This is a frequent case. So let us try to reduce the size of such frequent messages. Then even if you want to send it 10 times, you are not consuming so many bits, because its size is very small. So that is the idea. That is the intelligence in this algorithm. So initially I gave you an example when I talked about source encoding today, that if there are 4 symbols, let us represent it as 00, 01, 10, 11. That is very common, very easy, everyone can do. But Shannon found this idea. Probability of occurrence, let us code them variably, variable length. That is a groundbreaking solution several years before. That means when Shannon discovered such an algorithm, there were no such algorithms existed then. So this reduced the burden on the transmission systems or storage or processing systems. So I also gave you a hint that why we are thinking so much about the bits or the size of the bits, because when we want to transmit something, why do we encode? Why do we encode the message? For example, I'm speaking here, I want to encode my speech. Why? Because either I want to transmit it, or I want to store it, or I want to process it, right? So all these transmission, storage, or processing, they have a limitation that is called as constraint. For example, when you want to transmit it, you need to transmit it through a channel which has a limited bandwidth. You want to store it somewhere in a hard disk that has a limited space, 1 TB or 2 TBs, right, or some TBs. So we need to save bandwidth, or we need to save the storage space. So that's why we are worried about the size here. Okay, otherwise we can represent D by 10 zeros, C by so many 10 bits, no problem. But we have a constraint. By considering that constraint, your encoding algorithm should be intelligent. So we have variable encoding here. Shannon has done this based on the probability. And also these codes are unique, right? If you have 10 messages also, all the codes will be different. As a result, you can easily decode them at the receiver without any issues. So code word should be unique, that is done. And also they should be intelligent. Intelligent in the sense, it should be smart, not just assigning 00011011. No. So based on the probability, he has done that, and that's the interesting algorithms to study and think about, and that has become the foundation for many algorithms that came up after this in the future. Okay, this is the final step of this algorithm. So we also have to find out efficiency. Quickly we'll find out efficiency. So efficiency of this algorithm is given by eta s is nothing but h of s, that is entropy, divided by length of the code multiplied by 100. This is the equation to find out the efficiency. So you know how to find out the h of s, entropy, right? Pi log 1 by pi. This you have to compute for all the n symbols. What is pi? 0.4 log of that. Second message, 0.3 log 1 by 0.3, 0.2 log 1 by 0.2, and so on. So all these 4 messages, you are finding pi log pi and adding it. So that value comes to 1.4846 bits per symbol. And then what is L? L is nothing but length by considering the probability. L is given by this equation. L is equal to pi multiply Li. You know pi, probability, 0.4, 0.3, 0.2, etc. And Li also we have determined the length 2, 3, 4. Just you do this pi Li, pi Li, pi Li. So that becomes 2.4 bits per symbol. You just find out eta s, that is h of s, that's entropy divided by L, length, multiply by 100. So that comes to about 77%. So this says this coding scheme, I mean this example, using this example, the particular algorithm gave us 77%. But if you use some other example, maybe the efficiency will be better, because these values are from this example, not from the theory, right? So this is the performance or efficiency. Efficiency should be high, right? It should be 100%. That's the ideal case. Otherwise, it's okay, 77%. And then finally, we also had to find the redundancy. It was there in the question. Okay? Redundancy is what? RNS or eta s, that is equal to 1 minus efficiency. Here 1 represents 100%. Okay. Or if you don't represent it as percentage, then it is 1 minus ns is okay. Since we have represented it as ns as percentage, then it should be 100 minus that percentage. So remaining is the redundancy. That means the efficiency was 77%. So redundancy is 23%. So altogether that becomes 100%. So redundancy says wastage or unnecessary things, unnecessary overhead. So since the efficiency was not 100%, that means we could not represent all the symbols by optimum number of bits. We could not do that in that example. That's why we got an efficiency of 77% only. So remaining is a redundancy.